Can you hear me back there? All right, so I should be okay.
Minutes from the break. We'll do that. I'm guessing. Start? Okay. Hi, good morning, everyone. Welcome to the last day of our workshop. This morning, it's my pleasure to introduce Byron Boots, our speaker, who is currently at Georgia Tech, assistant professor in Georgia Tech, but he's moving to University of Washington. He's actually right now in the transition, so very soon he'll be here. He got his PhD from CMU and did a postdoc also at University of Washington before joining Georgia Tech as an assistant professor. He's an expert in robotics and machine learning. So happy to hear your talk. Thank you.
All right, thank you very much. So today I'm going to talk about this online learning perspective on model predictive control. This is joint work with my PhD students, Nolan Wagner, Qing'an Chang, and Jake Sachs. As Miriam just mentioned, I am currently at Georgia Tech, and I know I said this at a workshop recently, but I think it's true this time. So this will be the last talk that I'll give as a Georgia Tech professor, and in about a week I'll be at University of Washington. So until then, I'll have some Georgia Tech slides, and then I'll have to update all of the templates and everything. Okay, so I'm happy to take questions throughout the talk. So if you have clarifying questions, please let me know. If you think I'm totally wrong about something, let's talk about it, after the talk is over and we can have a long argument. But clarifying questions are great, and I definitely encourage them as I go through this talk. Okay, so as Miriam mentioned, I do machine learning and robotics, and this talk is really going to be about robotics in some sense, but I'm going to try to bring in some elements of online learning and model predictive control and look at how these ideas can be used to build super cool robotic systems. So I want to start by thinking abstractly about what a robot is. So here is a robot. I drew this when I was a grad student. And usually we can assume that the robot can perceive the environment and take an action which can change its relationship to the environment. So this is like your basic robotics paradigm that you see in sort of introductory textbooks. But for robotics that adapt their behavior with experience, we may want to break down this diagram a little bit further. So usually we call the function that takes states or observations as input and produces actions as output a policy. And the policy itself has some parameters theta here. And if the parameters stay the same, then the robot's behavior stays the same. So when it encounters the same state, it'll act the same way. But I'm interested in robots that can learn from their mistakes and handle complex dynamic environments. And in this case, we can specify some sort of learner that updates the policy parameters in order to improve at some task with experience. And the task objective function, which is the J up here, basically tells us how good the policy is and guides the learner in this process. Okay, so this is one way of thinking about an adaptive robotic system, where really we've highlighted this difference between like the robot and the environment. We're thinking about these two things as kind of separate and interacting with each other. But alternatively, we can actually focus on the learner. And here the learner is interacting with a complex system consisting of the robot in its environment. And we can actually think of this setup as something like online learning. So just a refresher, in online learning, just kind of general framework. In round K, the learner plays some decision. In this case, the decision is the parameters of some policy. An adversary selects some loss function. The learner suffers the loss and updates his decision for the next round at K plus 1. Okay, so why does this framework make sense for robotics problems? So I want to step back and think carefully about how robots should learn. So empirical risk minimization is in some ways the dominant paradigm for thinking about machine learning problems. It's often used to guide how we think about very basic machine learning problems like classification and regression. But my claim is that it doesn't really make any sense whatsoever for robotics problems. So first, robotics data is not IID. So robots collect data which evolves over time, and they interact in closed loop with their environment. So basically what this means is when a robot takes some action, it changes the distribution of data that its sensors can see. Second, analysis like statistical consistency, which I've myself have used quite a bit in the past, don't really make any sense at all for robotics. So generally, the models that we try to learn in robotics are necessarily approximate. So the data generating process typically does not live in the model class that we're trying to fit. And then finally, data is not batch, but is instead streaming and collected through interaction with the environment. So rather than kind of thinking about this way for doing machine learning, we can think about online learning. And unlike empirical risk minimization, online learning makes minimal assumptions. And it mainly focuses on the concept of regret minimization. So we're going to think about two types of regret minimization today. So for stationary policies, where we want to learn a policy that works everywhere in the environment, minimizing regret basically means learning a sequence of policies that compares well with the best policy in my policy class in hindsight. So in other words, I want to learn rapidly. I want to do the best that I can given my policy class and the data that I've seen so far. For non-stationary policies, I can think about this as trying to learn a policy sequence that is performing as well as possible with respect to the best sequence of policies that I could have executed. And this type of regret is much harder to minimize. So online learning focuses on notions of regret like these, but it's also very general in that it does not make the IID assumption. And online learning is agnostic with respect to the ideal system. So I'm just trying to learn the best policy in my policy class. So that's kind of the high-level, somewhat hand-wavy reason for thinking about online learning in robotics. So next, I want to look at just a few well-known online learning algorithms that attempt to minimize static regret. And after going through some of these online learning algorithms, we'll start to talk about the robotic system and how we can apply some of these ideas. So really, the simplest algorithm in this area is follow the leader, right? So the basic idea is that if I find a set of parameters that has minimized the sum of every loss function that I've encountered so far, then this may do well in the next unseen loss function. So in other words, I choose the best policy in hindsight. And for well-behaved loss functions, follow the leader can achieve on the order of logarithmic regret. In the worst case, though, follow the leader algorithms can severely overfit the data, which leads to some undesirable behavior. So to contend with this problem, we often add a regularizer. So for example, we can think about this regularizer as something like the Bregman divergence here. And this prevents the solution from changing too much in between rounds. So the choice of regularizer generally depends on the problems that you're trying to solve. But common regularizers include things like quadratics, the Fisher information metric, KL divergence, things like this. I also want to just mention that instead of minimizing the sum of regularized losses directly, we often reduce this problem to a simpler problem where we focus on linear loss functions. And the linear coefficients g here basically are just forming an inner product with our parameters theta. And this still can work for a wide range of problems. We can just choose gi to be like the subgradient of an arbitrary loss function, li. Okay. Finally, we can get to mirror descent, which has strong connections to follow the regularized leader, as well as the gradient descent family of algorithms. First, we can interpret mirror descent as basically a lazy version of follow the regularized leader. Basically, you're only minimizing a linear approximation of the loss function at this round, combined with a strongly convex regularizer. So let's just look at a toy example if you're not familiar with this. So here the goal is to find the minimizer of a convex function f. And we can do this by using mirror descent with a quadratic regularizer, which gives us this optimization problem at every round. And the eta here basically tells us how much we want to regularize. And if we take the derivative of this, set to 0, and solve for x, then the solution to this surrogate problem is exactly a step in online gradient descent. So again, note that eta here plays an important role as the step size. Okay. And different divergences result in different algorithms. So for example, if you use the Fisher information metric, then you get natural gradient descent, et cetera. So again, this is kind of high level, very quick, try to understand what mirror descent is without going into too many details. All right, so now I want to talk about some less well-known online learning algorithms. So mirror descent attempts to learn a sequence of policies that compares well with the best policy in my policy class in hindsight. So over multiple steps, it should converge to, for example, this optimal policy theta, so something like this. But an interesting question is, what if your best solution is changing over time? So for example, maybe I have something like this policy in a very simple policy class, and at every round, the best policy might be different for each state. We'll get to kind of some details about that, but you can just imagine that the best policy is sort of changing something like this. So in this case, what we might want to do is attempt to minimize tracking regret. And we can do this with an algorithm called dynamic mirror descent. So at every step, dynamic mirror descent updates a surrogate loss function like vanilla mirror descent, and then uses a predictive map to anticipate the next parameters. And if the predictive map accurately captures how the comparator sequence is evolving, then dynamic mirror descent should have low regret. So let's see how this works. So at the current time step, we can take a step of mirror descent. Next, the optimal solution moves, and we anticipate the move with our predictive model. We then take a step of mirror descent. The solution moves again. We take another step of mirror descent and keep repeating this process. So if we have a good enough predictive model, then dynamic mirror descent converges towards and tracks this comparator sequence. Okay. So at this point, I just want to step back and kind of remember what we're thinking about. So we're talking about online learning. We're going to think about it as a perspective that unifies algorithms, that explains empirical performance, and will suggest new approaches. In particular, we're going to think about how algorithms like the ones I just covered relate to some interesting robotics problems. Okay, so that's enough math for the time being. Now we're going to see how to use this to solve these awesome robotics problems. So here's one of our robots. This is a high-speed off-road ground vehicle built in collaboration with several labs in computing and aerospace engineering at Georgia Tech. Just to give you an idea of what this vehicle is, so it's a 1/5 scale truck, which means that it's about 1 meter long, so it's about this large. It weighs about 50 pounds. It has electric motors with a top speed of about 60 miles an hour. It also has cameras, IMU, GPS, LiDAR, wheel speed sensors all on board the vehicle. And then it has considerable onboard computational resources. So it has an i7 processor, a GTX 1050 Ti GPU, and it does all of its sensor processing and decision-making on board the platform. We can also control this vehicle by steering and modulating speed with throttle commands. So we're generally thinking about like these two commands. And our task is what we're calling terrestrial agility. So we want to drive this thing on dirt tracks or off-road as fast as we can, hopefully faster than a human pilot can pilot it, and do it without crashing. So thinking about this from kind of the AI perspective, we want to think about how do you design a policy that will pilot this car at superhuman speeds over rough terrain and do so without crashing. Okay. So why is this hard? So what I'm about to show you is a slow motion video of the dynamics of our car as it's taking a turn at high speed. And what you'll see is that the car is bouncing and sliding. And this is resulting in behavior that is very difficult to predict and virtually impossible to simulate accurately. So if I just kind of write down a simplified model of the physics of this vehicle, this is very, very difficult to kind of capture these dynamics. And if you get the dynamics wrong, or have a policy which even makes a small mistake, then you're in serious trouble. And the problem here is that the errors in your predictions compound, and they cause the car to generate bad behavior. So what you're seeing here is the car oversteering, and at fairly high speeds, this can be fatal for the vehicle. Okay. So how do we actually control a vehicle like this? And one good place to start is with classical engineering. So we can decompose this problem into individual unit-tested components. In our current setup, the pipeline looks something like this, where we have a perception module, which basically consists of differential GPS and IMU, which give us accurate outdoor position to within a few centimeters. We're doing state estimation on board the vehicle, so we have a map which is computed with a GPS survey of the environment, and then we're localizing the vehicle with respect to that map. And then we're also going to assume a system model, and we're going to use model predictive control in order to generate actions. So the system model in our case is a combination of learned neural network dynamics and known kinematics of the vehicle. Okay, so the overall pipeline looks something like this. So for those of you who aren't familiar, I just want to briefly mention how model predictive control basically works. You can think about model predictive control as a very pragmatic approach to designing a policy, where we don't even attempt to build a stationary policy which works everywhere in the environment. But instead what we do is we use a very simple policy class, and we re-optimize this simple policy very aggressively. So this is going to be our interpretation of MPC. And I'll show you how this will work. But at this point, I just want to mention that this seems a lot like online learning, right? Where you can think of the learner, which is interacting with a complex system, which is comprised of the vehicle interacting with the environment. And as many grad students who have worked with this have found out, you can think about this as your adversary, which will choose to do things which may be unanticipated. Okay. So are there any questions at this point about sort of the vehicle or the setup to the problem? Yeah.
So maybe we'll go into this, but will you be talking at all about kind of like how do you parameterize the policy class?
Yeah.
Yeah. What's a time unit?
That's right, that's right. I'll talk about all of those things on just the next slide. So, okay. So what I'm going to do now is I've sort of divided this slide into two halves. And on the left, we're going to have the online learning paradigm. And on the right, I'm going to give you some examples of how you can kind of think about each step in online learning. And the examples are going to be related to our experiment. A little bit later, I'm going to show you some more general examples, but I'll get to that in a moment. Yeah.
Very high-level question.
Yeah.
Why are you talking like there are much closer models than the online learning, like online MDP, UCRL? Why online learning? Why not take the more MVPs in an online setting approaches?
Okay, yeah, so that's a great question. So why don't we leave that to a little bit later, and I'll try to show you how I think online learning, and a little bit more specifically for MPC, dynamic mirror descent is an interesting framework that provides some insight into some of these problems. But I'm happy to discuss that more maybe a bit later. Okay, but that's an excellent question. Okay, so all right, so let's kind of think about some of the questions that you were just asking actually about what are time steps, what's a policy. So we're going to first think about every round of online learning as corresponding with a time step in the system. So what this means is that the learner is going to pick a new policy at like every time step. So in our case, it's going to be at about 60 hertz. Okay. Second, the policy could be anything, but for like our platform, it's going to be a simple open loop control distribution. And we can think about this as basically a joint distribution of trajectories of actions. And this will be just sufficient to make a sensible decision at the current moment. So note that when I'm thinking about a policy this way, it's just these open loop sequences of actions, and it's not conditioned on the state of the system. It's literally just a distribution of action sequences. Okay. So again, this is not required, but is going to be the sort of policy that we think about for kind of comparing model predictive control algorithms. We're also going to assume a simplified biased simulator that takes the current state of the system and the control distribution as input and produces a distribution of states as output. And using a dynamics model, we can integrate this state forward in time. And you can see this sort of here in this figure, right? So we have our open loop control distribution of actions, and when we combine that with this simulator, which we can think of as something like a dynamics model, that takes this open loop distribution of actions as input and the current state, and then gives us this distribution of states. Our objective is then going to be the expected cost under the simulated state action distribution starting from this current state ST. And this includes terms like stay near the center of the track, drive as fast as possible, minimize acceleration, kind of the common types of costs that you see in robotics. So now one of the things which is kind of interesting is that you can view the environment as selecting a loss function for our policy, and it does this by generating a state. So the idea here is that our loss at time t is just going to be the robot or the world putting our robot in a particular state in the simulator. Once we have that, we're then going to evaluate our control distribution at that state. And this is adversarial because the world can kind of put us anywhere in the simulator, including places which we might not expect due to limitations in simulation. So we'll just think about this kind of idea of how you're evaluating that control distribution as you're proposing it, and then the world kind of tells you where it's going to put it, and then that's your adversarial loss function. Yeah.
So you said that the policy doesn't depend on like any sort of state. But then, okay, so in the picture you're showing here is like, if you follow this policy, like the distribution of where you would end up after so many time steps. So if the track, for example, like took like a hard left and a hard right within like this kind of rollout that you're looking at, so the policy would need to actually do different things, like you can turn left and turn right. Would that make sense in this framework? Or?
Yeah, so it's a little bit subtle. So basically, the idea here is going to be that the policy is not going to be like a conditional distribution, which is conditioned on state, but this distribution is going to be kind of updated between rounds. So there will be previous information sort of in there. So maybe this will become clearer in a moment. But another way of thinking about this is like, okay, I don't necessarily know exactly where the simulator or where the world is going to place me in simulation. I just have some policy. So for example, if I have an open loop policy which results in a state distribution which is basically kind of straight, and the simulator places, or the world places me here in the simulator, then that distribution is going to have low cost. If I took the same distribution and the world places me like right here, then my distribution will sort of look off this direction and you'll end up with like very high cost. But I'm making this like decision about like what my distribution is before I actually am placed somewhere in the simulator.
Maybe it helps that in these open loop things, that you see you're constantly replanning.
Yeah.
So you take one action, even though it's open loop, you would never execute this forever. You replan.
Yeah, so we'll kind of see how this works, but Shyam's right. Okay. Okay, so then from the online learning perspective, next we want to update the parameters of our policy based on the loss. And our goal is to try to do something like minimize tracking regret, although for those of you who are more theoretically minded, we're not going to prove anything about that. Okay. So to accomplish this, we're going to use dynamic mirror descent, which I mentioned a little bit earlier, which is, again, designed to minimize tracking regret. And remember that dynamic mirror descent has two steps. So in the first step, it's going to perform mirror descent to update the control distribution so that it has lower expected loss on the objective, meaning that it performs better in simulation. And if the cost function of dynamics is complicated, we might actually approximate this gradient via sampling. I'll come back to that in a few moments. So again, what this will do is it will result in an updated control distribution that performs better in simulation for the current state ST. Right, so we've proposed this open loop control distribution. We put it, the world tells us where in the simulator we're going to be, and we update that distribution so that it has lower expected cost for the current state. We're then going to execute by sampling a first action of the updated control distribution. And then the second step of dynamic mirror descent comes in, which is the dynamic part. And this uses a predictive model to shift the distribution forward from time step t to time step t plus 1. And then the online learning algorithm will move to the next round, which plays the open loop control distribution together with the next state, updates the policy with dynamic mirror descent, and then keeps repeating. So at every round, you're trying to kind of fit the control distribution so that it works well at the current state. You're trying to sort of predict a good distribution for the next state. Then the world chooses what next state you're going to be in, and then we'll keep repeating. Dale, yeah.
Yeah, so I think this is quite interesting, right? Because now you're basically in the loop. You're embedding the learning dynamics as the critical component of how the agent interacts with the environment. And so, like stability arguments and any sort of like theoretical arguments, you now have to reason through the learning dynamics, not just the state dynamics and policy.
Yeah, so a lot of the stuff on model predictive control doesn't really deal with precisely how well the model is like approximating the real world. Right? You sort of just assume that your model's pretty good. But one thing which is very interesting here is that really what we want to do is try to think about having a model which is potentially very suboptimal, and kind of what this means in terms of how you should be adapting your control distribution and what you should be expecting in terms of where the world places you in your simulator. So like if you're just doing stability arguments based on like dynamics or something like this, you're also assuming something about how good the fidelity of your simulator is, right? And we actually sort of want to get away from that in some sense. Yeah.
So you still haven't told us what the policy parameterization is going to be. Is that going to be important, or why do you need to choose a distribution of actions? Why not just go with a sequence of actions?
Right. Okay. So the policy can actually be parameterized any way you want. So let me give you some examples. So an example for like an open loop control distribution would just be mean and covariance. So it's like a multivariate Gaussian, right? Another example might be I have actually something like a deep neural network, and that might actually be something which is closed loop. And I'm not really going to talk about that, but there's no reason why you can't have like a closed loop policy which is also conditioned on state as part of, as the framework they use. You could also imagine having something like just a sequence of actions. So we'll call that like a deterministic policy that you're updating. And that's something which is a little bit more like LQR or something like this. But any of those is actually okay in this framework. Yeah. So I'll talk about kind of comparing some of these and like how various known MPC algorithms can like fit into this framework and how you can compare them and view them. And you can also generate new MPC algorithms, as I'll talk about. Yeah.
I'm very confused.
Okay.
Like, what is the model and what is the algorithm? And the real question is, suppose I want to do a better algorithm. What is, okay, and I want to change it completely. What is the interface that I'm seeing? This is sort of, there's a mix here of a model and an algorithm, and I have a very hard time saying, this is the model, go and write a different algorithm for it. This is my algorithm.
Yeah.
So if I want to write an algorithm, what is my interfaces and what's my benchmark that I need to do?
Okay. So right. So there's a number of design choices that you can make, and so what we're going to talk about is basically different design choices which I can make, which kind of correspond to different aspects of a model, and then the algorithm that we're going to use in order to optimize our objective is going to be dynamic mirror descent.
No, but, okay, doesn't make any sense.
Okay.
I want to choose the actions the way I want to choose them. What is the model and what is the performance criteria? You can't tell me, okay, you have to choose a model and you have to do it this way. No, I want you to do it my way.
Okay.
There's an algorithm and there is a model. So what is the pure model?
Let me. Okay, sorry. So let me come back to this. Again, let me kind of.
I don't understand anything.
Well, so I'm gonna try to be very.
Yeah, where we are.
All right. So let me move on to at least the next slide, and then I will attempt to address this. Okay. So first of all, the way that like model predictive control works is also quite complicated and has like a number of hidden assumptions and things like this. And I'm hoping that this will actually elucidate things. We'll see, I guess. But let me tell you kind of what I want. So let's move on to this slide, and then we can continue to have this discussion. All right, so we're basically viewing model predictive control as an online learning or optimization perspective that exposes certain knobs that we can turn to derive MPC algorithms. So we're going to make a number of choices, and through those choices, we're going to get, if we try to optimize with something like dynamic mirror descent, whose goal is to minimize tracking regret, right? That's the objective that we're going to think about for the optimization algorithm. Then you're going to get different MPC algorithms as special cases. So here are the basic things that you can design for a particular problem. So you're going to choose your policy, which is going to be some control distribution. And as I mentioned, this could be deterministic, so it could be a sequence of actions. It could be a Gaussian, categorical, exponential distribution. There's different ways of parameterizing this policy. Then you have this objective function, which is going to be the objective in simulation. So you're going to be thinking about, exactly how you want to parameterize that objective in simulation. I'll talk about some of these specific choices, but this could be something like a quadratic objective or other types of utility functions. So these two things kind of correspond to, and then you're going to be given basically a simulator, which that's just going to be given to you. And then once you've made these choices, you can make some choices for optimization. So you can choose a particular regularizer, which might be one of these different Bregman divergences, and the step size. And then you're going to use dynamic mirror descent in order to optimize. Is this clearer or not?
This is an algorithm, it's not a model. I think when we... I want to run a very different algorithm.
I think maybe...
Out of
I mean, you can do whatever you want, but I'm basically providing a prescriptive framework which allows you to generate model predictive control algorithms as special cases, and will tell you how to compare them, and also tell you potentially why some work and why some don't. Yeah.
What might help with the data switch? I think the setting is one where you have a simulator, something like a generic model of the world.
So I want a definition of a simulator, a definition of the regret, and a definition of what the different algorithm, and then a proof why this algorithm sort of beats other algorithms.
That's too much.
So you're asking for something that...
First.
Right. So we provided a definition of like tracking regret, okay? And the definition of a simulator is going to be any function which takes the current state and a control distribution and generates a state distribution, which you can evaluate with your cost function, which is something that you design. Yeah.
I have a different question, but it's probably related. So
Okay.
you're gonna place this into the control loop. State estimation is going to estimate the state, and you're gonna feed that to the simulator or into this algorithm at some point, right?
Yeah.
But it's a little bit unclear to me, like how does that feed into the algorithm? How does the state information or state estimated state feed? When is that point?
So
Because you said that like the
yeah.
adversary
So
thinks like
this
the
whole
state, but
algorithm.
it's like,
So this whole algorithm is a control loop, right? Like so, this produces a closed loop controller, and so the place that the state estimate fits in is that like first I generate this control distribution, then I am going to estimate my state action sequence with my simulator, given the state that like the state estimator gives me, right?
okay, so that's the adversary is
Exactly.
actually the environment. Okay,
So the adversary, you should think about this loss as basically the state estimator is injecting this state into my simulator, which is kind of telling me what loss function I'm going to be evaluated on. So for example, if the state estimator places me someplace in the environment, I can get different losses, right? And I might get a much better or worse one depending on what my current control distribution is. Yeah.
And what's your file going to be that you use in dynamic mirror descent? Are you hand designing that or how does it work?
Yeah, so we'll, so which, yeah. So, right, exactly, okay. So this could be anything, but for MPC, what we're going to use is we're going to use like a shift forward operator, which is going to basically extend our distribution by one time step and then like marginalize, right? And generally this will be kind of a shift forward, and if it's a Gaussian, it'll be something like a shift forward and an increase in the covariance, right? So you can think about it as something almost like a Kalman filter or something like this.
Yeah.
Yeah.
Just to make sure I'm following, so if the state jumps around arbitrarily over time,
Yeah.
there's no way to do this. So you're sort of imagining that.
Right.
In this scenario where the state moves
your
slowly,
predictor,
starts-
like the better you can predict, basically, where the like next state is going to be. Theoretically, the lower regret you should have. If you can't predict that, you're screwed. Yeah.
It's not really the state, but like what actually is happening.
Yeah. If the state
Right,
sort of
right.
view the places where you're actually in no sense. So you're just trying to say kind of for any arbitrary sequence, it's nice enough. Things will
Yeah.
happen.
Yeah, benign in like.
So there's 5 minutes.
Okay. Okay. All right. So I just want to show you that when you make different choices here, you get different algorithms as special cases. So there's some pretty obvious ones like online gradient descent, where you can kind of set these to anything, but you're using a quadratic Bregman divergence. Natural gradient descent, where you're using Fisher information. You can have an exponential family control, where you're using an exponential family distribution of open loop action sequences. You can get LQR by using a deterministic distribution, a quadratic objective, a quadratic Bregman divergence, and a step size of 1. You can get bang-bang control by using a discrete categorical distribution and a KL divergence. You can get the cross-entropy method by using a Gaussian distribution, a threshold utility, and KL divergence, and a step size of 1. You can get model predictive path integral control. It's basically very similar to CEM, but with an exponential utility, and many more depending on whatever choices you want to make. So here's just a really kind of simple example. You can tackle different cart pole problems with different versions of this framework. So if the cart is actuated with continuous controls, then you can just use a generalization of model predictive path integral control with varying step size. But if the cart has discrete controls, you can just simply swap out the Gaussian distribution for a categorical distribution, and exactly the same algorithm will work. So for our experiments on like the rally car, we're using a generalization of model predictive path integral control. Our control policy is a Gaussian distribution, and our loss function is something that we call an exponential utility. So basically, here we're sampling trajectories from the Gaussian distribution of actions. We run each trajectory in the simulator. We integrate it forward in time to generate a state action trajectory, and then evaluate the state action trajectory's cost based on a cost function that we designed, which is the function C here. We then exponentiate the negative of the cost of each trajectory. And if the costs are high, this results in 0. If the costs are low, it results in a high score. And the loss is then the negative log of the expectation of these scores. So we have higher cost if the distribution results in no good trajectories, and lower cost if there are many good trajectories. We need to get all this to work on the real system in real time. So in order to do this, we use a GPU. This algorithm is naturally parallelizable, so when we sample a trajectory, we can roll it out on different cores of the GPU. And this allows us to simulate almost 2,000 trajectories, which are 150 steps long. So looking at 150 time steps in the future at about 60 hertz. Once we've computed the trajectory rollouts, we can use dynamic mirror descent to update the policy parameters, which in this case are just the mean and covariance of the Gaussian. The main parameters of the update are, again, the Bregman divergence. We use the KL divergence here, the step size, which controls the amount of regularization, and the predictive map, which, as I explained before, is just a simple shift forward command that shifts the mean of the trajectory forward and increases the covariance of the Gaussian policy. So you can see what this looks like when running on the real system. Basically, we compare running the car on this dirt track to one of our grad students piloting it. He's actually been racing these cars for about 10 years, so he's quite good, and we can get about a second faster than him. And we're able to do this because the car is able to anticipate things like drifting through the turns and handle the dynamics in this slip regime in a way which are very, very difficult to actually simulate well for a vehicle like this on a surface like this. Okay. This strategy is very effective in general, and it transfers to more complicated tracks. So in the first track, you just saw it was a circle, but here it is able to turn in 2 directions. It is able to handle hairpin turns by basically automatically figuring out how to slow down, and then it's able to race fast by speeding up on straightaways. So it can work for a variety of tracks and surfaces. The surface here is changing over time.
How does the simulator know about the track?
So we basically have a map of that environment that we compute using GPS and LiDAR, and then what we can in advance. Yep. And then we're just localizing against it quickly. Yep. We can also modify the cost function, so to transfer the strategy to more complicated tasks. So here we're using LiDAR to identify objects in the track in real time, updating the cost function, and then using this updated cost function in order to avoid obstacles as the car is racing around the track. Finally, MPC in general is fairly robust to perturbations. So what you're seeing here is the car coming around the track. It's drifting through this turn, and you'll see there's a small rock which knocks the back of the car out of alignment, and the algorithms are able to recover from that sort of perturbation and continue driving. So just to summarize, dynamic mirror descent and using it in this model predictive control framework basically uses online learning as a framework for understanding MPC. It shows how classic MPC algorithms are related to one another, and also provides a prescriptive method for designing new MPC algorithms. You can do things like use Laplace distribution if you want samples which are from a wider tail distribution, and you can vary the step size. There are parameters like the step size in mirror descent which are actually hidden in the original MPC derivations, and this suggests that many of the off-the-shelf MPC algorithms are actually suboptimal. They make a number of heuristic choices which are unjustified. A common example is that the step size parameter in these MPC algorithms is generally just 1, where instead it should be tuned or adaptive. I'll just kind of quickly show how that can really help things. So I won't go into the details here, but I just want to show you an example where we've reduced the number of samples by 2 orders of magnitude. And in this case, running vanilla optimal control algorithms like MPPI or CEM actually causes the car to crash into the boundaries of the track. Again, we're just using 64 rollouts rather than 2,000, and you get this fairly suboptimal behavior. You even get some weird stuff like the car will turn around and start going the wrong way. But by adjusting the step size, we're actually able to effectively navigate the track with only a small fraction of the number of rollouts. And this is super important in practice on things like embedded systems and robots with higher dimensional controls. So you can imagine manipulators which have at least 7 degrees of freedom, or walking robots which have up to like 54 degrees of freedom. And we have some new results and that sort of thing. Okay, so if you want to read some recent papers on online learning, mirror descent, and MPC, which are coming out of our group, there's a whole bunch of them here. If you want to learn more about what I talked about today, you can look at this paper, An Online Learning Approach to Model Predictive Control, which recently won Best Student Paper at RSS. I want to thank the students who worked on this. So again, these are my PhD students, and this is the paper to look at. If you have additional questions or want a copy of the slides, feel free to email me at my new email address at University of Washington. So just please email me about that. Thanks.
Thank you. That's it. And since we are running late, I would say let's keep the questions for the break. The next speaker is Vikash Kumar from Google Brain. He got his PhD from University of Washington, from this department, worked with Emmo Todorov, and has been is a research scientist in Google Brain, and has also been at different places like OpenAI as well. And we are very excited about his talk. It's going to include very cool demos with 2 robots as well. So looking forward to it.
Everyone keeps your fingers crossed. It's robots, you know. We'll need all the help in the crowd.
With HDMI, do you want to go USB-C?
USB-C. I don't have HDMI. All right, I'm looking good. Awesome. All right, great, thanks. All right, perfect. Oh, goodness, okay. All right, I'm very excited to be here. It's nostalgic to come back to the place that you learned so much, and then I have something to share, so it's exciting as well. I've learned two things over the last 2 days. If your advisor is speaking at the same workshop, it's a nightmare for you, because he tells half the story and then shits on the rest. So I'm going to try to pick pieces somewhere from what he said and some of the pieces where I think we have been able to move past some of the challenges. And I think Byron Talks is very much aligned with those challenges, and we will see like what the parallels are, what the lessons are. Some of the differences from previous speakers that I want to highlight right away is I'm not trying to prove anything. These are merely data points of how far we have been able to push. Absence of something here doesn't mean it doesn't work. It just means that I haven't tried it. You all should try it. Okay? So these are data points of how far we can push the complicated system. Some of the differences in the applications will be that these are really high-dimensional systems where you cannot form any kind of simulator, much like what Byron was mentioning. We are talking about dimensionality roughly between 60 to 100 dimensional spaces with a lot of deformation. There is no rigid body assumption that is probably valid over there. And the second thing I want to also point out is the state distribution shifts quite a bit. So unlike Byron, where like you're going on the track, this is like you can't really visit the same place again, almost those kind of settings. And as if you guys haven't noticed, these are all pictures of hands. So this kind of gives you the diversity of the things a manipulator of this dimension can actually take. So this motivates problem very nicely is if things are that nasty and that complicated and that's your state space, let's figure out what's possible. All right, and I'm going to be talking about something what we take as granted privileges, I'm calling them. A lot of people just take assumptions. That's another word that we use commonly. And I'm going to be highlighting a spectrum between the model-based and the model-free side of things. So we'll see how things are, where they are in the applications and the areas that I'm interested in. So fair bit of reality check. Amo talked about this in his talk. We roughly did this in 2012. And things work in real time. You probably saw movies where you can toss things on the ground. It beautifully gets up. It does cartwheel, and we all clap, and it's great. But if you do reality check, this is what things look like today. And this is coming from Boston Dynamics, which is known to get things to work, right? It's trying out things to place things. It topples. There are wheels. The cart falls down. Everything that can go bad will go bad. Basically, that's the sad reality. So what is the difference between the two? And one of the key differences between the two systems is on the left, when we got these results, we have perfect access to the dynamics of the system. On the right, you have no access to the dynamics of the system. Let's just relax it a little bit. You know kinematics, you know somewhat of the dynamics, but the reality is so far away from what you can estimate, what you can simulate, that things like these are inevitable, it will go wrong. Okay? So my arguments here will be trying to see that like how we take some of these performances from here and try to move there.
I just want to contrast this to Byron's talk, because the lesson from Byron's talk to me was that if you're computing online at a very high frequency, then even a very crude model can go a really long way. So I was wondering, like, okay, these guys are really high tech, but like, if you increase the frequency more and like, you know, maybe just throw in more computation, and it is going to do it.
I'm with you. Let's make that argument together.
Yeah.
All right, I'm follow along with that argument. Yeah. So I'm just going to make the point that like this is the reality in the way that from hardware experts that they know how to get things working still are struggling based on the best they can do. All right, and there is a reason, and like we are going to ground those into actually scientific challenges and see how we can make progress in those dimensions. This was the picture that Emma showed to motivate a lot of things. And question I want to ask here is like, how can he even build a model of this thing and then do all the nonlinear trajectory optimization that he preached the religion here yesterday, right? And the answer probably is not very clear. It goes somewhere along the direction of what Byron also mentioned, that like, yes, model is very impressive and concise representation of information, but getting access to it is incredibly hard. It's a powerful piece, but how do we build that? How do we get there? I think that's where the key is. All right, so I'm going to build up a couple of results, and I'm going to put them in a spectrum. On the right, where we have no access to the model, which is the bot, like I'm saying red, and on the left, when we have full access to the model. And we will see what works, what doesn't work, how far things are along this spectrum as a data point, not as a proof that these are the ceilings. All right, keep that in mind, because these are very personal related to the work that I have done.
So when you say full access to the model, you mean like?
I have a full simulator.
And that simulator is accurate?
So let's just say the system I can query and the system I'll execute is exactly the same.
Okay.
That's, yes.
Yep.
So the first one is you have full access to the simulator. You can query the simulator at any rate you want. I'm going to call something over here as 1x sample. That means during the execution time, how many samples do you need to execute versus how many samples do you query to execute. So this can be executed in real time. I'll go a little bit more into details into this in a little bit. And I think very well motivated by Byron, online trajectory optimization, optimal control has been incredibly successful in these domains, but you have full access to the model. Roughly the way these settings work is there is a robot model, which is a fully global model of the dynamics. You can query, it will tell you exactly what happens in the next state. There is assumption of a state estimator where you know where you are, where the state is, and then you present goal using some intuitive cost functions. You hit it with an optimizer, optimize really, really fast. You get behavior, so iterate over and over again, and you deploy these things in an online model predictive control settings. I think we heard about that a lot. Roughly speaking, the way this works is you're at some point, you want to make a plan, you want to execute a little bit of it, and it's like, oh, the world is not exactly the way I thought it would be. Let's make that step, and let's plan again. So you just kind of iteratively update the thing. And there was a little bit of discussion that Byron put forward is like, why does MPC work? I think roughly I agree. There is always a plan. You keep re-optimizing the plan. If the world behaves differently, so be it. You just iterate and go forward. Using these techniques, we have been able to show very dynamic movements of the order of like this. Roughly, the dimensionality of the system we are talking about is about 60-dimensional system. We have full access to the ground state full access to the dynamics function over here. The objective here is there is a hand, which is about 30 degrees of freedom. There is a 6 degree of freedom object that randomly falling in the scene. Your objective is to stabilize the object. That's what you know, that the object has to be up there in the air somewhere, and all the details of the movements are automatically synthesized. You do not tell anything about the details of the movement, so that's the beautiful part. When you have access to the dynamics, we have planners that can do amazing things. And you will see it fails. It's trying to slip, and it kind of re-optimizes, which is like one of the lessons that fast re-optimization can give you a lot of things. And if the another beautiful part of this is it's a reusable machinery, which is also something that we want to do, that we want a machinery, a framework, an algorithm that can solve multiple things. It can take the same machinery, we ask it to do typing, just change the goal state to something that says typing, and you can on the fly keep updating the goal. Since it's constantly replanning, it adapts, it kind of does like nice things. You can apply perturbations, replan, etc. Things glorious, everything happy, robotics is solved, we can go home. All right. All right, so like I want to take my take of like why I think MPC actually works and it does make sense in the real world. When we are executing, we are never executing to the optimum. So even if we know how to get to the optimum in a provable way, probably doesn't make sense to spend that compute to go to the optimum. You're only going to you're only going to execute for a little bit, so your best bet is to get a good plan in this like small narrow horizon. So focus your compute over there, get the best update you possibly can, and leave everything to hope. But can we do better than hope? Yes, you can do better than hope, which is what we call value function. You put the value function at the end, and that kind of gives you the hope. You extrapolate based on the hope. But the thing is, we overfit to the current situations, and you just hope that that kind of carries forward. And then replanning does the magic for you. But the challenges here are that if the value function is not good enough, you do start getting stuck in local minima. But that's the problem today. I have no answer, but that's the reality. That you do get stuck in local minima, and if you have a better value function, you have a hope to get out of the minima. So over here, what we just said that like once you have full access to the dynamics, we can use gradient-based planner that exploit the dynamics, give you really, really fast recompute power so that you can execute these kind of behaviors in real time, which I'm calling 1x number of samples. If you have access to the dynamics, I also showed you can generalize one setting, different settings, throw different cost functions, that's fine. I will probably say that these kind of assumptions and settings are only possible in simulation. That's why I'm putting a label simulation over there, that it works in simulation. If we want to run it in the real system, the access to the dynamics function, the true dynamics function, is not available. So the benefits that we get from gradient-based and MPC planner cannot directly transfer in real world. Questions? All right. So before filling the spectrum, let's take to the other side. Completely other side, where we have no access to the dynamics function. What we are going to do is we are going to do just completely model-free RL, and we are going to build a policy that exactly solves the task that we are trying to solve. So what will happen is we will get what we want to do, but nothing more, nothing less than that. And the best thing we can hope over there is we generalize a little bit on the thing that we want to do. You can't do anything more than that. And the beauty over there is like in these constraint settings, things do work on the hardware, but the sample complexity is incredibly worse. You will see while these things work in 1x samples, they take like maybe 10 to the power 4, they're slower 10 to the power 4, because you're just sampling the system over and over and over and over, and that kind of exhausts the system. I'm going to show you some results which have been presented in the work over here. But I'm going to motivate it from a little bit different standpoint. If some of you were here yesterday, Emma showed this amazing graph where you have a flat basin, where you have no gradient information, you can't really move, and then there is a really nice shape over there. If you push over there, you can optimize. But the problem is that pushing in this good space is hard. And if the space of hand and manipulation is that high dimensional, that it becomes incredibly challenging. So for most of these things that we are going to talk about right now, we solve this problem by adding a little bit of demonstration that kind of focuses you into the right area, and then we'll let the optimization do the magic. Okay? So those are the two ingredients over there. If you ask if we just have access to the demonstration to focus you in the right space, why not just do behavior cloning, et cetera, et cetera? There is a small restriction or budget I'm going to enforce myself that I'm going to use a really low number of demonstrations. It's 25 demonstrations, somewhat manageable. Your budget is right. You can kind of get those demonstrations easily, even if it takes a lot of work. You can just have 5 people like hold the robot and do 25 demonstrations in a way. But the problem of just doing behavior cloning is that if it has to work, it will take a lot of demonstration to work. If you execute, the state mismatch is going to be too much, and you will run into compounding errors. This is never going to execute in the real world properly. And if you ask the question why this is happening, is because behavior cloning is just trying to solve the wrong problem to begin with. It's trying to produce the optimal action given the demo distribution instead of the induced state distribution. When you execute, you don't remain in the demo distribution. You go out of the distribution, compounding errors, everything, you drop the object, everything fails. You're crazy. But what it does, it just puts you in that right space where you can actually focus your exploration and then fine tune from there properly. So what we say is what you do is you do your policy update. The top is the policy update, and the bottom is you also add a function which asks you to stay close to these demonstrations. And there is this weighing function that you just anneal away over time. And that kind of gets you started. So in the beginning, the top policy update will not give you any information because you're so far from doing anything meaningful. Only thing you can hope for is like staying close to your demo distribution because it's taking you to the right place in the subspace. And as you start annealing away the W term over there, then it says that like, okay, I'm in the right space, I can throw away the demonstration, I don't really care what was proposed to me, but I can use the power of like sampling, updates, policy updates to go beyond what was demonstrated to me. And that will be critical because you don't have a lot of demonstration. 25 demonstrations in these high dimensional spaces mean nothing. And in these kind of settings, we have been able to show that you can do fairly complex behaviors of the kind where you don't only have a manipulator, which is high degree of freedom manipulator, but the manipulator is also interacting and understanding these various objects and their target configurations. And dealing with free object is somewhat subtle and it doesn't really work. And it's hard to understand why, but there are some intuitions I can share, is the base of the arm is working on a very large space. And the fingers are working on a really small space. So there is this space mismatch between the two, and the coordination needs to happen is that the arm really needs to coordinate, and this precise action needs to go exactly at the right time for all these things to come together. Because you will, when these things are being trained, you will see the arm going the right place, but the finger not doing the right thing. When the finger tries to do the right thing, the arm is in the right place. These kind of local minima are very prominent in these problems. So yeah, like we can do picking of balls, we can use different kind of tools, opening the door. The dynamics here is primarily dependent on the door, so you can't really overpower the door. So these are interesting things. Another interesting aspect that falls out of this is roboticists has been trying to get to human-like behaviors for a really, really long time. And they're trying to enforce it in a lot of different ways. Velocity constraint, the jerk free, et cetera, but these are all approximations or understanding of what we think human-like means, right? But if you have these 25 demonstrations I'm talking about that implicitly encode what being human-like mean. So this kind of falls out for free almost, that it gives you the right inductive bias to be like humans. So if you see on the right side, you will see like these artifacts are very real if you do a lot of shaping and get things to work. But like, yeah, it gets the job done. But that artifact that we are looking for, like what it means to be gentle, nimble, being like human, almost comes out for free, which people have been trying for a really long time. And these things do tend to kind of make, the addition of demonstration do tend to make the policy a little bit more robust. I'm not going to go into details, but we check some robustness characteristics on the right, and the higher it is, the better robust it is to both the axes, which are different perturbations to the system. So now I'm going to start filling up the gap in the middle. Okay, but before we start, any questions? All right, either everything's clear or nothing. Great. So now the question is that I'm very much proposing that access to the model is critical and nice. And I'm trying to get more and more access to the model, and I'm going to start building this model because access to the model automatically or from a simulator is just not the reality of the world today. Okay, so let's see how we can build a model to the system. So in this case, what we are going to do is we are not going to focus on developing a full model, but we are going to focus on developing a model which is very rudimentary in the sense that it's trying to exactly learn the model around the things it's trying to do. So what we're going to do is check out that robot box, which was the full physics model. I'm going to start substituting that box with a partial model, which is a time-varying linear model parameterized directly on the sensor data. So we are not talking about joint angle positions or nice properties of velocities, etc. Whatever is your sensor, we're just going to go for the sensor data. And that's where we are going to build the model. And we are going to adapt as we go on the model. So very briefly, let's look at the right. What it's trying to do is if you have a policy which is time-varying on the time-varying model, we are going to query the policy to give us the actions that it wants to take at the moment. We are going to execute those actions on the real system. As we have the actions, we are going to update the model. And we are going to keep doing it over and over.
So is this basically just like model identification and depth control?
You
like
can
a neural network model?
This
I know
is
the details for
yes.
what matter, but
Yes.
Yes. Okay.
Yes. So we are trying to make a simple model that we can quickly adapt with less amount of data. And the beautiful thing over there is going to be that we are picking the linear model in a way that we can run gradient-based optimization on it to actually get the good effects of MPC on top over there. Essentially, everything I said, except one part, it's kind of important to bound the model update by a KL. And this is because you don't get to query the real system quite a bit. So if you make aggressive updates, there is a very good chance that you're going to fall really, really far off. And even if it is one bad update, it's going to take you somewhere really bad, which you can't recover. So if you bound this with the KL, and the noisier your system is, the tighter you should keep the bound. And if the system is better and better behaved, you can relax and make it bigger and bigger. So that's kind of a human intuition over there that goes how closer the bound should be. Let's start looking into a demo, what we can do over here. So again, a human hand shaped robot. What we are trying to do is trying to rotate free-floating object in the space along different axes over there, X, Y, Z, and you can see over there. And most of these behaviors are learned with 60 trials. So we are not talking about thousands or even millions, thousands. We are talking about just 60 trials. And agreed, these things are very simple. We are trying to do simple things like rotation, but if you see the kind of behaviors it need to exhibit in order to get those things right, it's quite complex. The pinky has to push, the middle finger has to pivot, the thumb has to get in and out of the whole system has to stabilize, because initially what you'll see that it will just drop the whole thing. It doesn't even understand how to stabilize the system, and it'll start dropping the system. And it is general, again, in the same sense that you're building a model. Given the model, you can do a lot of things. And since you can build a model easily, benefits of MPC, you can repurpose all of those things into like different behaviors. Over here, here is roughly like each iteration is roughly like 5 rollouts. So about 12 is about 60 trials that we have done. So what we're able to show right now is that an extremely sample efficient process. It can work with contact dynamics, which presents a lot of constraint in the actual dynamics. So these are not smooth dynamics, and it does work in real system. But there is an interesting thing that is going on over here, that it did converge over here, but what did happen here? So what we ended up doing in this case is like you start the system at the same place initially because it's not good. So you want to help the system by starting the system more or less in the same place, and it's updating its own estimate so it iteratively gets better and better. But the moment you think that it has gotten better, now you start destabilizing the system. You don't reset, or you reset in a very noisy way, and those perturbations you see down there are exactly it's trying to adapt the learned behavior, the learned policy to the real world realities that, yes, the system is never going to stay in the same place. You have to adapt based on that. And it does learn a really robust policy, but around the task that we are trying to do, it doesn't generalize to a different task. Sorry, yes?
So how did you learn the local linear models? Like you learn them for every time step, or like?
Correct. So basically we start with a uniform policy that just random perturbations. There is a task. So given the task, given the model, You optimize like just ILQG, LQR, you can do all those things, pick the actions, execute those actions, you have a new model, and you update the based on the task. Yeah.
And iterative.
Yes, iterative.
Learning control.
Correct. Yes. So we did 12 updates over here. Each update's collected about 5 trajectories in this case.
And what's the starting policy where you
Just random policy.
wait?
So like, yeah,
Uniform
uniform policy. Yeah.
But you drop you just keep dropping.
It just keeps dropping, yes. Initially, just like, you'll stay there, it's uniform policy, it just like flops because the weight of the system weight of the thing is too big, so it starts stopping, it tries to move, and it just falls.
And you have the starting simulator.
There is no simulator involved here.
I see.
So directly on the real system, from step 0, the first data was collected by a random policy putting the object on the hand, and it's now trying to do like
But you
just
have part of the model like with your actuators and sensors.
no,
right?
nothing. Input to the system is completely raw potentiometers values from the joint angles, and the action space is a little bit more convoluted over here because we are going through pneumatics. So there are pneumatic channel. We don't even have a model for pneumatics. We are directly controlling pneumatics at the voltage at the valve.
And what's the size of the state dimensionality?
100 to 112. So we have all the joint angles, joint velocities, the pneumatic pressure, because that's a third order system, so you've got to add that pressure into the system, and the first order derivatives of that, and information about the object. Yes. Yes.
There is no tactile sensing.
No.
Lump figures.
I can discuss that. There is a very strong belief that it will help. I do believe it will help, but I have never been able to show that it actually helps. And there are hypotheses. I'm happy to share that off.
Wait, I'm sorry. So what's the variables for the object? So the angle is
So the object is just a free. It knows the position and quaternions of the object.
Okay.
Yes.
Okay.
Yeah. So it's not sensing the object using touch.
And that you just have some video that tells you.
Correct. So this is in a motion capture setup.
Okay,
It just
okay,
gives
okay.
like positions and orientations of objects.
In what sense is the regression local?
In the sense that it's optimizing exactly for the tasks. So the way the policy and the model updates, that it actually updates where you solve the task and it just forgets everything else.
But it's a full LQR model.
Correct. But local in the sense of trajectory that it is planning to get the task done.
Okay, not per state. or per
No.
state.
Yeah, like the whole state vector. Yeah. Okay, so in this case, what we are able to like, in this case, what we did, we built a local model, we learned that model, and we used the good properties of a model over here, which are the gradients, and we did it better than what we did in the model-free settings. It's still not real time because we have to go through the 60 iterations to get more data. There is no generalization in this case, but things are robust for the task that you are doing. We didn't get any generalization because we have no idea what happened outside the task distribution. It does work on the hardware. Okay, so we are going to move a little bit on this side of the system now. That we are going to start learning not local, but partial models now. Okay, and let's see what the details over here are. So the details are somewhat weird because this is under review, and since I am no longer in academia, Google lawyers tell me that I can't share the details. So in assumption that no one is going to tell Google lawyers anything about this, I'm going to give you some details. Okay? Hopefully no Google people are here to me. So I'm not going to give full details over here, but enough to actually make my point. But if there is something not clear, please ask me offline. I might be able to share some more. Okay? So what we are trying to do here is we are not trying to build a global model. We are trying to build partial models. What are these partial models? We don't know, but we are going to build an ensemble of partial models. And it's important why it's an ensemble. I'm going to tell you a little bit about it. Each of these models are represented by a neural network. Just feed forward. We have tried LSTMs, have not been able, it works, have not been able to show that they're a little bit better, or even a little bit better than the feed forward ones. But I do believe that we haven't pushed it hard enough. So I think we're going to do it there. So what we are going to do here is the same settings as the previous one. We can only interact with the system in a reasonable budget. We can't like interact with the system way too much. What we are going to do is based on this collection of the data set that we get from the interaction, we're just going to start fitting an ensemble. These ensembles are different ensembles with different seeds, so they will behave a little bit differently. And it's important here to build ensemble because what happens is as you update the model of the system, they do not capture the reality very well because you don't have that much data to capture the reality in these high dimensional spaces. So we are using an ensemble as a proxy of how good the real world, how good understanding of the real world we have. If all the ensembles tends to give you the right update, the same update, that means that we have captured the system well over there and we are going to trust that update. But if all the ensembles tend to differ in what the predictions are, that we are going to say that we don't understand the system at that point, and we are going to, in next iteration, prioritize getting those samples better. So that's our metric of where to sample and how to sample. In previous one, the way we sampled was just directly shot for the policy. Where policy was trying to take you, we went there. But in this case, we have a weighted way of sampling where we are asking the policy, what is the task update? Push me in that direction. I want to build a model over there, but we also want to say that if I don't understand the system in some place, I do want to sample over there to build an understanding of the system in that place as well. And that's how the whole thing goes. And in this case, we are able to show that we can learn models that generalize. It's not really task specific, but it generalizes roughly in the same family of tasks. So if you're trying to, let's play some videos and I can share some insights over here. So here we are trying to turn this three-finger valve, oh my goodness, the picture, is to the target. And that was marked by the green spot. And the next one, we are trying to rotate the cube in different configurations. Right? The target is marked on the right. So those are like, so for the rotation task, if you try to rotate and learn a model for like 90 degrees, 180 degrees, you learn the model and it generalizes to other parts of the state space because it's trying to learn a partial model of what it means to rotate. It's not trying to learn a trajectory in this case. So we are getting access to the dynamics model that you can retarget by changing a cost function later, as long as your state visitation roughly remains the same. If the state visitation differs too much, you can't do much. All right? So in the case of the cube that I showed, that we did a lot of like side turns, this turn, that turn, and it generalizes to the other turns that we have never showed data about. Okay? And the beauty of this is that now there's a lot of ablations which are not going to go into details over here, but the important part is the green lines on all three of them. That it is ridiculously sample efficient for higher order or more difficult tasks than a lot of the sample on policy as well as off policy methods that are available today. It doesn't work for everything that on policy, off policy can solve, but at least for the settings that we have been trying, it is ridiculously sample efficient. And it does give you some generalization in roughly the same task family. So yeah, I'm sorry there's not a lot of detail I can share, but like if there are some high-level questions, I can try to take that right at the moment. Yes?
This idea of learning generally how to rotate as opposed to learning a trajectory, does it go kind of does it go both ways or does it go one way? For instance, if I'm learning how to rotate a cube, I have to learn how to rotate on a lot of dimensions. So then maybe if the next task was to just spin a pen, I could do that very well, but would it not go in the other direction? If I just learned how to rotate a pen, I might have trouble learning the cube. Like, does it make sense to start with a harder task in terms of rotation, and then it generalizes forward?
It does make sense. Provided, so here we are not really giving the detail of what the object is. So if you're learning this model in like a full point cloud space, then it will actually understand. But as far what we have tried is we have put a tracker on top, and then we have learned just in the state space, and we haven't given geometric information of the object, which gets implicitly embedded in the model at the moment. But if you learn it more generally, I do believe it will actually start transferring. Yes? All right. So that's, and let me bring in a little bit more towards the learning the model, learning a more global model. And this is somewhat that came in discussions on Monday that I alluded to, so I ended up adding this thing in there. There is a very interesting insight over here that we are going to learn skills over here, but I will explain how it falls in a model spectrum over here. So we are going to learn skills. There are a lot of different ways people have thought about skill, and we are picking a different intuition about the skill. So let me start from there. That the way people have looked into skill is you collect a lot of data and you do PCA, and those PCA dimensions are kind of somewhat like one way of looking into skills. Dimensionality reduction is another way of looking into skills. The way we are looking into skills is not just in state dimension, but we are looking into skills into state cross time dimension. Okay, and the way we are calling something as a skill is if you can predict yourself, you are a skill. So predictability in the dynamics is a skill. That's what you're calling. It's pretty bizarre, but a lot of good things come out of this. All right, so the intuition is that if there is a skill, the state distribution, the state action distribution is somewhat constrained in this. You can learn this more easily, but the problem becomes now that there could be so many random things that you can learn over there. How do you make sure that you learn the right skills? That's basically the challenge. So that if you can somehow magically find the right skills, then you can actually, these things will be useful. And there are prior work on this, like Dion and stuff, if someone is familiar. The differences there are is once you learn those skills, you don't know what to do with those skills. We are going to learn here with the dynamics function so you can repurpose these skills. Sorry, yes?
One of the core issues here is that, like, if my sensors are vision and I shut my eyes, then I'm very well predicting my future state, and I'm sitting still and not doing anything, and that's not a very good skill.
Yeah, you're going to learn that skills. Yes.
Right?
Yeah, you're going to learn that skills. Intuition about positives of this skill is think of someone juggling. Even if you close their eyes, they have skills that they can use to roughly juggle the right way. Not exactly.
I guess the question is, like, how do you, like, there's so many, as you say, so many different skills to learn. How do you encourage the system to learn at once?
Yeah, we do end up learning a lot of bad skills.
Okay.
It is falling out automatically. That's why we don't care. But you're exactly right that we end up learning skills which are really, really bad. It has nothing to do with being useful. Okay? And one of the ones.
The system on the top doesn't care about that. Like, just sorts them out.
Correct. Yes. So the thing which one of the skill that you will actually like go down into is just staying still, because staying still is the most predictable thing you can do. Okay. So without going too much into the math over here, I'm going to give a general idea. We are parameterizing skills by Z. Also, we are parameterizing skills by Z. The dynamics function of like the skill dynamics, what we are calling skill dynamics, is given a state and the skill, we can predict the state transition. That's what we are calling skills. And the beautiful part of like using this mutual information objective that has a lot of details in there, but is that the skill and the controller of the skill both falls out together. That means given a state and the skill, you know what actions to take. And roughly things go down this way, that like what we are trying to do is if you given a state and a skill, you want to maximize the predictability of the next state. At the same time, what you're going to do is you want to say that like the next state predictions given a different skill should be different. So this is the diversity term and this is the predictability term. So you are incentivizing different skills to be different, and within the skill you're incentivizing the predictions to be better. And yes?
So you're not expression, mathematically, what is Z? Is it a policy?
No, Z is basically a label. That's a skill. In discrete setting, Z1, Z2, Z3 are different skills. In continuous setting, Z equals 1.1.2 are different skills. So that's my latent representation. If you
It's a random variable that's coupled with the state transition.
correct. And we have shown that it works both on discrete when z are discrete and continuous. Okay. So here are, like, if you ask, like, what do they end up learning, and then you will see that they end up learning pretty bizarre things. Like it doesn't make sense for a lot of things. A lot of things they will just like sleep and not do anything. All right. So they do learn, like you're saying, they do learn a lot of like weird things. And like here's some pictorial representation of a lot of them overlaid on each other. But like if you look into what they're learning, we started looking into some of the feature space. So here is the orientation of that ant. And if you, like, there are two dimensions, Z1 and Z2 in this case, you will see that there is some structure that they actually learn in these, the couple of good feature space. So they tend to do like good. But like, yeah, like a lot of them are like, it doesn't make sense to us, but that's fine because these are learned totally unsupervised. We haven't done anything. It's trying to go on offline data that was collected from somewhere. We don't care. It outperforms a lot of model-based planning algorithms. And here are a lot of like model-based optimizations. Here are two variants, discrete and continuous. And then we just show that for like a lot of like goal-reaching tasks like these, where you're like using goals, and then it's basically searching over the skill space and choosing the skill that makes good progress towards the goal, and then like does the MPC style thing again. All right, so I'm going to wrap up like pretty quickly over here, and then we'll get some demos going over there. So what has happened right now? So we hit a spectrum, full access to the dynamics, no access to the dynamics. We were able to exploit a lot of gradient-based information when you had access to the dynamics. We got good access to the dynamics. A lot of gradient-based information gave us like good sample complexity. But I haven't talked about the sample complexity in these two settings not being that great. But we did have the skills. We did have access to the dynamics. So this is something which is bizarre, but it kind of does make sense. Since you are learning the dynamics model in a more generic way, the first order information of these dynamics are not preserved. So the moment you start using gradient-based planners, they actually tend to take you in random ways. And shooting methods tend to work better than any of the gradient-based planners at the moment. But this is fixable, I think, that when we learn the dynamics model, we have to kind of somehow figure out how to preserve the first-order derivative, second-order derivative information, which I think is a good next step, but I don't think it is that easy at the moment, but we are looking into it. All right, questions? All right, cool. So where things stand together, if the model-based and model-free really depends on where you are. I heard a lot of great insights over the last 2 days into that if you really take things to the limit infinity, there are great things that we can prove and show in some of the system. But in true reality, what I'm going to argue that it does matter where in the spectrum you are. If you're here in the spectrum, the choices are very biased towards one side of the settings. If you're on the other side of the spectrum, the choices are very different on the other side. But you're in the middle, I think there is a good class of algorithms over there that can be designed to take insights from both places. And this is where a lot of algorithms like Polo, for example, that was talked yesterday, falls. You can try to combine the benefits of partial model as well as model-free settings, and then you get more accelerated methods in that intersection that I mentioned, yes.
So why do you think that model-based is losing at the high sample rate G? Because the model is not accurate enough, even if you give the parameter?
Couple of reasons. One of them is the model is not accurate enough, but if you think of what the policy optimization is doing, it doesn't care about anything else but to optimize for the policy. Right? It can overfit to performance, but if you're going for a model-based method, you're trying to get generalization, fit the model properly, and based on the best understanding of the model, you try to get better information. So there is a trade-off that the model-based method has to play, which the model-free don't have to. They can just like overfit to performance. Yeah, that's a great question. Okay, so this is, I poked into one direction of these things, which I call privileges or assumptions, which was the dynamics. Oh my goodness, it's not visible, but this is a very interesting graph that you can ignore now. But there are lots of other things that starts to matter. And when we start to put everything into perspective and start plotting your algorithm, how they lie in these curves, then the area under the curve starts to matter. And for real system, that is the metric that people care about. That is the way the real systems move forward. So I was having this conversation with Miriam and Alec yesterday that like, as someone who wants to push on what is the best or the highest level of things we can solve, we often come into the constraint that one of these axes are super great, but because of the other axes being super bad, the area becomes large. So it's important to think of like the trade-off, and in a budgeted and constrained settings, if we can get better algorithms, I think that will go a long way. That's my key message over here. Yeah, this is, by the way, I want to show that like how resets, for example, are taken as granted, and it takes up either 4 months for you to design a reset mechanisms or a grad student to spend 4 months to do the reset for you. And this was me as well when I was doing the cube rotation, the tube rotation thing. So yeah, a lot of these things are the real bottlenecks now that the algorithms are trying to scale and actually go out in the real world. I think a lot of these assumptions are really where things are weak, and we need to hit them hard. Okay, so the demo time, I'm going to give a short spiel on what the demo is, why it is important. Like I said, there is these huge spectrum and axes on which we are trying to minimize the area of all the algorithms, right? But it becomes important to actually be able to probe those settings equally well. And this is not where I'm trying to solve DARPA robotics challenge. This is not where I'm trying to do Atlas backflip. This is basically think of pure science and trying to minimize the area of this curve. So in those settings, I think I take intuition from the domain of physics, where what they did was design something that was called an optical bench. Most of the Hubble telescope, electron microscope, etc., those intuitions were first tested over here, and they led to bigger developments when people scaled and found the right fundamentals. This is what I think is somewhat missing for robotics right now, that everyone is trying to do a lot of things where things are different, and there are a couple of platforms on which I'm trying to build my intuition, and I'm going to share these things with you guys, and starting today, it's going to be public and online, so feel free to share with everyone. These are robotics benchmarks for learning. These are benchmarks. There are some important, interesting things over there as well. So let me try to like just show you really quickly. There are few benchmarks there are few hardware platforms which are very modular. The interesting things about these platforms are that these are modules that you can reconfigure in any ways you want. Here are the 3 settings I've shown you guys, but if you have different applications, just go for a different application. Just the same thing is going to work for you in terms of software, hardware settings. It's really easy to reconfigure all of those things. That kind of gives you the optical bench illusion that take a lens out, put a lens in kind of a setting. There are 2 platforms. One of them is called the Claw. Another one is called the Kitty. The good thing about these things are that these are modular. You can compose any number of degree of freedom. These are super cheap to build, so advisors, please spend some money. Give your students one of these. $3,500, $4,200, great things. In my team, everyone in my team has one on their desk, and the kind of experiments they run is bizarre. Like, you will have never thought that anyone who will ever run experiments are running experiments right now. One of them is Sham's student, Arvind. If you ever ask Sham, Arvind will touch a hardware. Sham, will Arvind ever touch a hardware?
He's supposedly doing that now.
It's correct, because these things are easy to use, and that's how it's easy to use. The best part is that the price point scales linearly with the degrees of freedom. So you can try to build a more expensive system. And the reason I went down this route is I work with a lot of high-dimensional systems. And these high-dimensional systems tend to break frequently. The shadow hand, I fix every 2 days. It is ridiculously expensive, and I can't really send it back to London every day, so I have to build these systems. To the date, these systems have over 15,000 hours recorded on them without breakage. So that's great. I'm going to quickly gloss over some results on that. Please refer to the videos and papers associated with them. They scale incredibly well. You can pack it in a backpack, take it with you. Here are some flexible object manipulation you can do with them. Here are some disturb intersections you can play evil. They know how to take care of themselves. You can take one of the systems out. You know what they can do. Things are pretty scalable, parallelizable. We are learning multitask over here, different objects. They're setting different settings, and then they're learning together how to learn how to turn, etc. Here is the walking robot that can walk over anything. Literally, you give it on the way, get caught in the wires. It can go over all those things, push things on the way. We have been walking it outside, indoors, you name it. Here is a paper that we recently published where we let a couple of them out in the wild. They learn how to interact with objects. If you give big objects, they learn how to coordinate within themselves and do good things and better things by trying to figure out how to make both of them move together. There are some benchmarks that for you to get started, good software, everything for you to like just get it ready and go in an hour. Okay, so without getting too much bottled down here, just a last point that like, yes, these systems have resulted in a good collection of results so far from a diverse group, so kind of making the point that they are widely useful, which you can take a look into. Cool. And then let's do the demos. All right, so in the first one, what is going to happen is the top one is a target, which you can start picking yourself. If someone wants to come pick a target, they can definitely come and pick the target. And the policy is trained in a way to start matching the target to the best it can. The bottom axis is really slippery. So if you just like do something like simple, it just follows like. All right, so you roughly get the idea of like what is going over here. All right, so I'm going to be a little bit quick over here and go to the next one. I can play these more later if you want to come up after. Here you just randomly let the top thing pick a random number generator on the top. It's trying to pick a velocity and a target, and the bottom one is trying to actually match the best it could actually do. And we can hit it with any algorithm. You can study different algorithms. It is robust, self-sufficient, independent, that you can run most of these things remotely. We do run everything remotely. All right, so that's a manipulation platform. We just took the same thing, put like 4 of them down there, and that's a locomotion platform now. So I'm going to make a fool of myself here, but be with me because there is no tracking in the room. So it is completely running blind, but at least I can probably show you is the policies that we have been able to learn on these simple systems are robust enough that it can at least stay upright, handle all of these things by itself. So yeah, it doesn't have any tracking, so it doesn't know like where the target is. I've roughly given a target which is in the front. So that's a reset. That's a reset. It didn't fall down. It's a reset. It's asking you to go again. So you see the kind of policies and behaviors that it exhibits. It's okay. Can you, no, don't do it. Pull the wire.
You should put a leash.
Yeah, I should push the leash. Yeah, I tried to put a reset so it doesn't go far enough. But look, like you saw probably, like here's a different friction, completely different friction with those, and it still understands how to handle those things properly. And these are the systems that I showed how to coordinate videos where we have like multiple of these systems. We have made a small house for them now where they kind of live together, explore the world, figure out where the kitchen is. The best thing is these are like, we call it the kitty, so it's a cat robot, but it doesn't poop, so you don't have to do anything to clean up the poop. This is great. And with that, I think I'll just stop over here. I think I'm a little over time. But feel free to come by later, and then I'll be happy to answer more questions.
Thank you very much.
Yes. Yes.
All right. Actually, I wanted to ask you this last week as well.
I'm really curious about what your thoughts are about this. So one of the things that you mentioned that's important to kind of look at is reset.
Correct.
And it seems like these benchmarking platforms are designed in such a way that if I make mistakes or if I perturb the system a small amount, it's basically stable. It doesn't necessarily trigger a reset, or like resetting seems very, very easy. And so I'll try to figure out how to kind of say my broader point. And it's not totally formalized in my head yet, but the idea, the thing that I'm a little bit concerned about is like a lot of the problems which are the hardest in robotics are ones where a small perturbation to the decision that you make results in potentially a catastrophic failure.
Correct.
So for example, if instead of having like a four-legged robot, you had like a bipedal walker, it's a lot harder to reset that system, and a small mistake causes it to fall over and require a reset.
Yes.
Another example is like the rally car. If you're in slip and you take the wrong action, reset might require rebuilding the car.
Correct.
Like this.
Yes.
So what I'm wondering is, like, do you think that there's a certain type of problems that these sorts of benchmarks, kind of like they make sense for machine learning in that it's easy to collect lots of data, and are those problems really the ones which are like the most interesting from robotics?
So I'll tell you my take. I don't want to advocate a right answer here. My take is that the more you have ability to ask those questions, the better off you are. Okay, I didn't show those results today at the moment, but we are running these robots in a non-episodic settings 24/7. They fail. When you start executing them, like they are floppy systems, like they don't know how to stand up. Like you saw trained policy, it will crash down. So it starts by doing catastrophic failures and then builds up from there. So it does, there is like details into this, well, feel free to browse around more, but there are like videos over here where we do learn a lot of like these getting up policies along the way as well. So it does like start from random places and tries to get up first. So it is trying to handle those questions. Can I actually design a reset policy myself? Yes. I can cheat the system, but I don't care about doing Atlas backflip. I care about minimizing the area on that giant spectrum that I show. And if you are careful and you're basically being optimistic, you can carve these problems out. That's what we are trying to do. We will be overfitting to this, but at this point, overfitting to the real world is a good thing to do, is my argument. Yes, we will scale, we will build a Hubble telescope from there, but it's not today. We're going to ask small questions today and then hopefully build from there.
Okay, thank you very much. Let's go to break until 11:05, so 15 minutes. Yes, thank you.
Thank you.
Very cool.
Oh, yeah, thank you. Yes.
Sure. Some waiver.
Sign your life. No.
All right.
So let's just say that I have a flight to catch in an hour.
Thanks. Okay, we are ready to start. This is the last talk of the workshop. Last but not the least, we have Csaba Szepeswari from University of Alberta, who is actually currently at DeepMind in Google in the UK, or you're back in Alberta.
I am back in Alberta since about, I don't know, more than a month ago, actually.
Oh, okay. Well, in both places. He's
Yeah.
doing very interesting work in reinforcement learning and machine learning, and he's done fundamental work in the area. Some of his older work on Monte Carlo tree search actually has been used in many places and recently won it Best of Test of Time Award. So we're very excited to hear what Csaba has for us. Thanks.
Thank you. Right, so this is the last talk of the workshop, and I don't know what even to say. Like, thanks for staying, first of all. After the talk, I will need to leave shortly after to the airport, but I'll try to hang around just a little bit more. But just as a heads up that I might need to, at some point, just leave. But I'm, of course, very interested in talking to you if we'll have time for that. If not, then, like email, all the usual channels of communication. Anyhow, so this talk is about recent work that I've been doing together with wonderful collaborators in Google Brain, Berkeley, and Yasin, who knows where he is. Okay. Next slide, please. Okay. Microsoft PowerPoint is not responding. Thank you. All right, that's fine. All right, so just to start, so I'm going to talk about, oh yeah, there we go. I'm going to talk about model-free RL and my way of trying to make sense of what is going on there. So we have seen what's happening. All right. Is this self-play or? All right. Microsoft's playing tricks with me. Yeah. All right. So I knew that I should use whiteboard. Technologies. Yeah, I know. I'm just wondering about whether it's going to play other tricks on me.
Probably. Let's go, man. We're
All right.
detecting noise. Csaba, we're detecting noise in your slides. Exploration.
Yeah, okay. Unknown territory, robustness. Okay, so we've been a bunch of results which were unexpected and coming from the combination of model-free RL techniques with deep learning. I can say at least that I didn't expect some of these results, and it would be nice to understand when these techniques work and how they work and what their scope of applicability is and whether we can improve them, right? So that's my goal in this talk, and that's the goal of this work. And so this slide is just used to contrast this model-free work with the model-based work, where we can also see MO there. And there is a lot of scope for both of these methods, but it seems that there is some nice corner. Maybe it's the large sample regime, but for model-free methods, but I guess it would also be important to reduce that sample complexity, right? So if you see these ridiculous sample complexities, or not sample complexity, but it's like the need for the compute, it's a ridiculous amount, then you must be wondering about whether there is a more efficient way of doing things or not. So that's what I'm after here. So any time in the talk, please, if you have any questions, stop me. So this is just a notation. I'm not going to use S for states. I'm going to use X. Right, and then I'm going to use A for actions. Yeah, it's like, just because I want to be a contrary, right? I don't want to follow any trends, right? Okay. Yeah, it's like if it has to be that like that, then it has to be that. Okay, so I'm going to make some assumptions here, and you might think that like they're innocent, but I don't actually know. So the state space is going to be countable, and that makes certainly easier to write certain things. Action space is going to be finite. I think I do have ideas about how to go beyond finite actions states, but the countable state space is going to be important at one point. It's kind of ridiculous. There's probably some way around that, but we'll come back to that. And to reflect on the first day's talks by Ben, I care about a case too, when maybe you don't observe, like the states as they are, like enumerated or whatnot, but you have a high dimensional observation, and maybe it's invertible, so there is no state aliasing going on. And you want to control the system to minimize the cost, and you care about the regret compared to like some other controller controlling the system. Maybe not the optimal controller. Maybe that's just too much to demand, and we'll see how that plays a role. So that's kind of the setup. Yeah.
So the comparison is to what? It's a different set of states?
Right. I mean, like it's a different controller controlling the system, so it's like a different sequence of state actions.
So you have a finite set of controllers and you're comparing to the best one?
I'm going to, like, it's like an individual regret bound, if you wish, right? So you want to be good against all possible controllers, but against some controllers, inevitably it will be harder to compete with them, and I want to see the dependence on the choice of this controller that I'm competing with to show up in the regret bound, right? It's like a non-uniform bound, if you wish. You can make it uniform. Like, the game is that you can make it uniform if you start to make strong assumptions about the environment, but okay, why? Why do you want to do that, right? So maybe a non-uniform bound is just good enough. All right. So this is great, but and this seems that like we are almost back to the tabular setting, but I actually don't want to do the tabular setting here. I'm really interested in when you throw in the neural network, and you use the neural network for value function approximation. And I will try to make an effort to understand, like, what can you say about these model-free algorithms in that setting when you have this neural network in the picture that is approximating the value functions. So that's why I can allow high-dimensional observation space, because I'm hoping that the neural network is going to take care of that, right? And I will make this quite formal, actually. I wish I knew how to go to the next slide in a seamless fashion. This is not how. All right, this is going to be painful. Just going to the next slide. It's not working very well. I have an idea. No, I just put this on and then. All right. Eventually it worked. Okay. All right. So let's start with some basics. So you can have these policies. They induce distributions over trajectories. And I'm going to be interested in, the total cost, and that's somehow related to the average cost setting. So I'm going to use the average cost setting for writing my equations. So lambda of pi is going to be the long run average cost of running policy pi against the system. And value function, in a simple case, it's just you just offset the cost with the average cost. And if you start a system from a given state, it gives you a value. And you can make it an action value function, and they're related to the value function. And the action value function satisfies an equation, which is just a linear equation in the average cost setting under proper conditions. You can show that this holds, right? Okay, so they're just getting the formalism out of the way. So people have seen the Bellman equation, and this is just to brief you about my notation. Any questions? It's good? All right. I forgot that I have to push the... Why? This has something to do with projection, because I tested these slides without projection. Anyways, okay. So before you jump into proposing an algorithm, maybe you should look at the objective that you're trying to control. In this case, we are trying to control the regret. And it turns out that there is a very easy way to decompose the regret if you bring in the average cost for each of the policies that you're executing at every time step, right? So this is just like almost a standard decomposition. So you can add and remove terms. So then you see that there are three terms that you need to control. So the first term I'm going to call the pseudo-regret. So that compares the average cost of the policy at time step t with the average cost of the competing policy, right? And then there are these other terms which are comparing the running cost with the average cost, and the same holds for the same type of terms for the competing policy, the policy that you want to compete with. And to control these terms, one thing to note is that you need to convert, since you brought in the average cost, you need to converge to the average cost. You have to let the system, converge to its stationary distribution or whatnot. So you might not want to change policies too fast. So the way to control that is going to be to use phases. And then if the phases are long enough, then that term is going to be well controlled. So I'm not going to worry about that term too much. Just keep in mind that you will need to introduce some phases. And there is some cost for changing the policies too fast. The last term that's completely obvious.
Maybe better if those as transients rather than noise.
Yeah.
Is that right? So this is the transient behavior before state.
Yeah. Right. I mean, it's both noise and transients. If you want to talk about high probability regret, then there is additional noise on the top of things. But Yeah, it's kind of the same thing.
Even a steady state picking up.
Even if there was no noise, the transient behavior has to be washed out. But I'm willing to make assumptions about like fast mixing at this stage, and just to simplify things. And so I'm not that much worried about like, and those terms, the only way you can you control that term is basically by introducing this slow changes to policies, and we're going to do that anyways. So the last term, it's out of our control, so let's not worry about that. So the first term, so that's the term that we need to control. And yes, we can control that term. Maybe the whiteboard would have been a better choice. All right, so that term can be controlled if we recall what's called the performance difference formula. This is pretty ridiculous. Switch machines? I don't know. Or end slideshow, restart, maybe. Oh. All right. So here we come. So the big help for dealing with the pseudo-regret is this performance difference formula, which I first read about, I think it was Shem studies, but there are some, wow, okay, look at that. No! This is a nightmare. Why? There's a huge lag, but I'm plugged in.
Why don't you use your laptop?
Okay. I can try.
Charles, I think sometimes PowerPoint has a delay, like just in the slide events,
Oh, that's probably right.
like 10 seconds or something ridiculous.
It seems that
You know what, is that in a setting? Yeah. Is that in a setting or?
I don't use PowerPoint, I got it once and I left forever.
Thank you.
Did you export the PowerPoint to PDF and then use the PDF reader?
Slideshow.
It seems like it's loading your.
This is not even just.
This looks like everything. Try moving back to screen.
Yeah.
There we go.
Just have to restart. So the performance difference formula tells us that the difference between the average cost of two policies can be expressed as this formula there. So here I'm using this inner product that just means that you're averaging over the states with respect to the stationary distribution of the second policy, and you're comparing the differences between the action values of the two policies. So one policy, the first policy and the second policy. So the meaning of these terms is that, well, I should probably not touch this thing because who knows what it's going to do. So the meaning of this notation when I plug in the policy in the second argument is that I'm just taking an average with respect to the state distribution at the given state according to that policy.
What is mu?
Mu is the stationary distribution under pi star, which I assume to exist for simplicity. Okay, so this is a very nice formula. You can rederive all of dynamic programming based on this policy iteration, everything. It's very, very nice. What's important for us is that this difference in the action values is a linear expression in pi. So here in the second argument, when I plug in pi, So that's just like an average with respect to the distribution that the policy induces. And if you plug back this difference formula into regret, and you write out what these inner products mean, what you see is that for every state, if you want to control the regret, for every state, you should be controlling this difference here. Okay? So this is the action value that you get if you execute your policy and the first action is according to your policy. And this is the action value that you get if you execute the policy, but only from the second step, and the first step is according to pi star. So there is one step difference between two. So this is really nice. It seems that we only need to care about controlling this sum for every state. Easy, right? Until you realize that the problem is that by the time you have to choose pi of t, the policy that you're going to execute at time step t, you have no idea about this function q of pi t yet, right? Because that depends on the policy. So you want to keep this term small, so how can you keep it small? You don't have access to the system. You can't really compute this whole expression. It seems that like to control this term is almost as hard as solving the full problem. So it's a chicken egg problem. All right. But here comes online learning to our rescue. And we have heard about online learning a couple of times before. How many people are familiar with online linear prediction? So just briefly, there is a learner and an adversary. And the adversary is choosing these loss vectors. And the learner has to choose one of the components of the loss vector in every round. And the learner's job is to control the regret against any choice of a component in hindsight. Okay? So even against the best choice in hindsight. And can we even do this? It happens that this kind of just models like it's a glorified and crystallized model of an IID word. It's like a generalization of IID, but it's not as hard as you might think, because you need to compete with the best single decision in hindsight, and the adversary doesn't have that much of a lever on you, because how can they make your job really hard to predict what to choose? Well, they can make the environment random, and that's it. Right? So in a way, the worst case environments for this setting where you need to control this regret are the IID environments. Of course, here you're not making any assumptions about the sequence, and the sequence can indeed be chosen in a closed loop fashion by the adversary. So the adversary can pick, well, cannot use your most recent decision, but it can use the previous decisions when it comes up with the losses. Okay? So the adversary can be reactive. Right, and so what is the algorithm to use? Well, there are many algorithms proposed. They come under very many different names. Exponential weighted average forecaster is one name. This is also an instance of follow the regularized leader. This is also an instance of mirror descent, and there are many other versions of these algorithms. And what is known about these algorithms is that they can control the regret. And you can get results like the following, which is taken from the book of Nicolo and Gabor. So this says that if you're properly tuning this exponential weighted forecaster, which is just, okay, in reinforcement learning would call this the Boltzmann exploration policy, then you can control the regret in a sense that the regret is going to be sublinear. So the average regret per time step is decreasing by time. So that's great. So you can get the square root T regret no matter what the adversary is. So how can we use this? So the way you can use this is that, well, we had this problem, And that problem, I told you, is just a linear prediction problem in disguise, right? So when you're plugging in pi_t in the second argument, that's just like an average. So it's linear prediction. So you can choose, based on this, based on what we have learned on the previous slide, you can just choose the exponential weighted average forecaster and use that as the policy. And if you do that, then remember what I said, that, well, you don't want to change the policies too frequently or too fast. On one hand, because you need to control the second term, and in the actual regret, and also because you don't actually know. So when you execute this policy, when you write this policy, you can write this expression for the policy, but where you get this action value function from, well, you need to estimate it, right? So one way of doing this would be to run the policy for a while, get some data, and then estimate its underlying action value function, right? So this is exactly what we're going to do. So we're going to run the system in phases, and in each phase, we're going to fix a policy. And we run that policy, collect some data. Based on the data, we're going to estimate some action value function. So we're not going to have access to true action value function, but some approximation to it. This is where the neural networks are going to come into the picture. I'm going to make some assumptions about what they can do. And once you have that, then you can plug in the estimated action value functions into the expression above and hope that the whole system is not going to collapse and is going to be stable, right? So obviously, the neural networks are going to introduce some errors, and you might be worried about that those errors are going to compound, and your system is going to break down. So that's the question. All right. Okay. So before we move on, so I need to know that I kind of like this very much, because it kind of tells me why, if you read the literature, recent deep reinforcement learning literature, people are really obsessed about putting these KL penalties everywhere when they're updating their policies. And the explanations that I'm getting from those papers are not totally satisfactory, right? Like, I don't quite get like why, like intuitively speaking, so one thing that they say intuitively, and that makes sense, is that you want to stay close to the previous policy, because if you stay close to the previous policy, then maybe you can reuse the old data and like you won't have any big surprises. But okay, so this is also telling me the same thing, right? So I should use something like Boltzmann exploration. Online linear optimization tells me that you have to regularize, stay close to the previous policy. So to me, this is like a nice way of trying to make sense of why people are finding that these regularization terms do help in practice. Okay, so what happens if we plug in this approximated Q functions is that, well, you got this expression in the regret that you need to control. And you can again add and subtract, okay, these terms. And once you do this, you realize that, well, you actually need to control the first term if the second two terms are controlled by the neural networks, like by how well you approximate. So the second and third terms are the approximation errors, the errors of approximating the actual action value function when you're running your value function estimation procedure. Yes?
So it just occurred to me, you're sliding something by, which is you actually have banded feedback, but you're learning a complete predictor and then treating the predictor as sort of complete feedback and running full information, no regret algorithm on top of the model.
I do have trajectory-based feedback. I'm sweeping under the rug everything that is related to how we are learning the action value functions at the moment. I will come back to that a little bit later, and we're going to discuss some pain points there.
But no EXP3, like it's just fully observed, like exponential waves.
It's like once you postulate that you have a black box that can estimate action value functions over the state space in some error metrics, so we need to use those, or we better use those error metrics over there, then right. So then you just have to focus. The next step is going to be to focus on how to fulfill that promise that we'll be able to do that. Yeah. All right. So, okay. So in summary, how does this work? So if you put this together, everything put together, then it's like you can say that this is an actor-critic method, where you're going to have an actor which plays a Boltzmann distribution with respect to the sum of the previously estimated action value functions. And then you run this in closed loop, collect some data. The data is fed into this other box, which is going to be the back box. I'm worried about that these are not the most recent slides that I have, but anyways, we'll see where you go at the end. And then based on this, you learn your action value function. Let's say you use a neural network, and every once in a while, you update the sum. And then you update your policy. All right. Okay, so up to now, if we put everything together, then we can read out the following result from just putting together what we know so far. That the pseudo-regret of this algorithm is going to be controlled as follows. So if you have errors in approximating the action value functions that are epsilon for each of the phases, then altogether you're going to have some error that's 2 times t epsilon. So it's linear in that error, but that's OK, I say. Because that promises that as long as you can keep those errors small, that the term is OK, it's growing linearly, but like that's life. And you also have this other term where you see that if you have longer horizon and E is the number of episodes. So if you have many episodes, then that term is going to be smaller. And you have this other term, which I alluded to at the beginning, which expresses how hard it is to compete with the policy that you use as the comparator. Okay, so there is the term. It's a little bit hard to read. The last term, that's the stationary distribution of that policy. And the stationary distribution is integrated against the log, the square root of the log of 1 over the stationary distribution. This is where the countability of the state space somehow comes in. And probably there is some way around that, but this is the best that I could do. And you can upper bound that by the entropy of the policy. So if that policy tends to go to some small part of the state space, then it's much better than if it's spread out everywhere. If it's spread out everywhere, then that term can be really large. OK.
What's L?
L, where is L? Oh, L is the abbreviation of log 2 over data, because it didn't fit. All right. These are not the slides. These are not the most recent slides.
How are you estimating the Q values?
I didn't tell. I didn't tell yet.
Oh, you haven't told
I
us.
haven't told, yeah. All right. So can I just play around with the slides a little bit? Because these are not the slides I wanted to use. These are old slides. Sorry. I hope that the slides, that the recent slides are saved. Like some. This is very dangerous. I think that these are, like, my slides were simply not saved. That's it. All right. So finally, if somehow you magically are able to control the errors such that after tau samples, your error goes down at the 1 over root tau rate, the error in approximating the action value functions up to some level E infinity, then you can optimize all the terms, the lengths of the phases and everything, and you can get a t to the 3/4 regret with all these other terms and the linear term at the end.
You have a linear term at the end.
Yes, you have a linear term. I mean, like, if every time step your wave function approximation is off by an epsilon, I think that the linear term is the best that you can hope for. Yeah. And so there, the hope is that you make the neural network larger. That term goes down. Goes to zero.
So Java, how are you thinking about sort of, so if you could approximate Q super well for every policy, you could kind of just do policy iteration or do some kind of...
Right. So the question is whether this has any advantage compared to just doing policy iteration.
Yeah, how are you
It
thinking
seems,
about
well, this proof certainly doesn't go through if you try to do it with policy iteration. If you try to do something with policy iteration, I feel that you have to have a much better control of the errors. So intuitively, my intuition is that what happens is that you're going faster by being a little bit slower here. So you're summing up the previous action value functions. So every episode can be a little bit shorter because of that. So you have larger variance for every episode, but since you're averaging, that variance kind of washes out. And since the episodes are shorter, you can switch more often, and you try to balance this in a careful fashion, which if you do policy iteration, then I don't know how to do. Yeah, it's like a smooth changes, right? Yeah.
Can the term, the 2 epsilon infinity, can it cancel out each other, the approximations? Because that is coming from the approximation error, right?
Yeah.
If it's not always biased towards...
Well, yeah, this could be pessimistic, but okay, I try to be optimistic, but sometimes it's just too hard.
Just to make sure I understand the setting. So this is so what's adversarial here?
There is nothing adversarial. I just use an adversarial argument to get a bound here.
Okay. And
right.
So what's different than the online MVP? So where's the
slide.
T to 3?
Yeah. So the online MDP setting. I think let's wait for the next
Okay,
slide.
just in terms of the setting, the assumption
In terms of the setting, it's different, right? Because here, in the online MDP setting, an adversary actually chooses the rewards,
right,
in an arbitrary fashion, and it's you know the dynamics, and based on that you compute the action value functions.
So what is the algorithm know here, just to make sure we're on the same page?
So the algorithm uses a black box that it can feed data to, which should approximate action value functions.
And the word is static?
And the word is static.
And what changes from data? Is this just optimization, or is there anything changing?
It's a fixed MDP. Nothing changes. The argument used the online MDP framework or the same idea to get, yeah. It's not really optimization, it's regret minimization, or I'm selling it as regret minimization. We'll come back to that.
Why do regret minimization? If you have the offline MDP and everything's static, why not just...
You don't know the MDP. You need to run a policy to actually get a sense of how well the policy is doing, right? So it's the online setting.
So you're estimating, you're estimating the Qs
The action value function is being estimated. So remember, when I explained the algorithm, the actor is running for a while, it's collecting data, it's feeding it to this other box. That box is estimating the action value function,
Oh, I see.
which is...
So this is some actually on policy
It's
method.
yeah,
and
it's
estimating
exactly an
the
on policy
queues.
method.
What does on policy mean?
On policy here means that we only demand the action value function estimator to work to estimate the action value function of the policy that is actually generating the data, not some other policy.
It's online. Just that
That's
that's right.
But it does that globally well.
Yeah.
If
Well, in
it's-
an L1 sense.
Right. So in
So it's
some
an
sense,
average. Yeah.
right, in some sense, the epsilon infinity is a function of the algorithm, right?
The epsilon infinity is a function of the black box. So my way of trying to deal with neural networks is that I just like close them off and I say that like it's someone else's problem to make this thing work, but to what extent? Huh?
This is not the question.
Yeah.
In some sense, if you're running on the trajectories that you see, if I never do action 1, you're
Yeah,
going to have a high error on
Right,
action 1.
Yeah.
So somehow epsilon infinity is a function of your algorithm and the way that it explores.
Yeah, absolutely. Not even epsilon infinity, the whole rate and everything. So, next slide, or 2 slides later. It's a good point. All right, so here I just wanted to show some history of like this kind of the same ideas have appeared many times in the literature, right? Like this algorithm is very close to conservative policy iteration, which is a very different setting, but it's like the same idea. Sham and Jones been working on this. So there the idea is that you're changing the policies in a slow fashion. It's a different way of controlling that. And you do this to compute a near optimal policy in a different setting. But it's kind of the same idea. Here as well, you're slowing down your changes. Another thing that's even closer, which already came up, is this online MDP framework, where you think that an adversary is choosing the reward functions time to time, and you have access to the MDP, and you're able to compute the action value functions once you offset the rewards. So in every round, at the end of the round, you offset the rewards. Let's say you're solving the shortest path problem or whatnot. And so in that setting, so actually the tools and the techniques that are used in this work are coming from this paper, right? Like it's exactly the same thing. It's just like regurgitated in a different way for a different purpose, but it's like the same machinery. We noticed that you can do this when we were working on QR problems, and we wanted to get model-free algorithms to work, right? There is a little difference because the loss functions under proper assumptions, under nice assumptions about a system, are strongly convex. So you don't have to use Boltzmann exploration or any exponential weighting. You can just follow the leader, right? And then you get better regret bonds there because the losses are strongly convex. So you can get this t to the 2/3 regret. And then it's also related to algorithms in the literature, in the deep reinforcement learning literature like MPO, which it doesn't have any theoretical analysis or backing, but it seems to work pretty well. Like people are really excited about these type of algorithms. So that's kind of why this is interesting to me. And then we have this work. And there's a bunch of other works, of course, which I cannot go into. And it seems that my slides are, like, these are really, really old slides. So I need to kind of reinvent myself against in the face of uncertainty. So one question was, like, why is this different than policy iteration? Good old policy iteration. And so I can't, like, this calls for a lower bound for that policy iteration maybe should be doing worse on some problems at least than Polytech, less control of the regret. And I don't have those lower bounds, but we were running experiments. And when we were running experiments, the obvious comparison was to replace the Boltzmann exploration with respect to the sum of the previous action value functions, just with the Boltzmann exploration with respect to the most recent action value function as the closest relative to this algorithm, right? So the classic, let's do Boltzmann exploration once you have estimated your action value functions. So this is on queuing problems, and the x-axis is number of phases, and the y-axis is the average cost for various algorithms. And LSPI is actually the exact same algorithm. This is linear function approximation. And my slides about how to, anyways. This is linear function approximation with the exact same settings. And what you see is that if you introduce this sum of the previous action value functions, you get a much more stable, much better controlled behavior, at least in these experiments. So it seems that there is a real advantage to doing this. It's not just like the theory is telling us that maybe this stabilizes this algorithm. It actually seems to work better. So here we are also comparing with another algorithm, RLSVI from Ian Osband and I think Dan and Zheng and Ben. And that algorithm is doing pretty well as well. So in some sense, like with some, so the different curves correspond to different tunings. Like we have a learning rate, this eta parameter that goes into the Boltzmann exploration. You can choose it different values, and we were interested in sensitivity and like what sort of performance you get across the board if you're choosing these values differently. And you can see that Polytech is not that sensitive, and it's pretty much on par with the other algorithms. So in this queuing problem, so what's special about it, why we're not, so this algorithm, I'm not claiming this algorithm is any clever in doing exploration strategies. It's not going to do the deep planning exploration. The problem that it may not choose some actions that it should choose, because Boltzmann is like, okay, in bandits we can make Boltzmann, it's kind of wonderful. You can make it a pretty good algorithm. For MVPs, it's not so clear that that would be the case. So we're not making any claims about that. We just observe that, like in some problems, maybe you don't need that much exploration. Like in queuing, it seems that the system is kind of exploring everything for you, and like the features are helping you. We have a more precise formulation, this in the paper with linear function approximation, but more recent work.
Just a clarification. So the Boltzmann exploration, so this is mixed in on top of the exponential weights. So you do exponential weights, and then after you get that distribution, you do Boltzmann on top of that?
No. I'm confused about what you're saying. Exponential weights to me is Boltzmann.
Oh, okay, that's what you mean by Boltzmann. Okay, so
I mean, it's the same thing. Exponential weighting gives you the Boltzmann policy,
okay.
right?
So it is just on the current estimates is what, there's no like an additional noise you're adding to that?
No.
Okay, fine.
Yeah. Well, yeah, we didn't do any of that. Yeah. Right, okay. Right, so yeah, like there is, but there are those problems where you need actual exploration, where you need to make an effort to visit places where you wouldn't just randomly get to. So what do you do there? We have a follow-up work where we are attempting to answer this question by introducing another black box. Okay, so we seem to be like, like you can't solve some problem, let's just make it someone else's problem. So they have to worry about this black box. And then once they solve their problem, then I can just take the black box and plug it into my algorithm. And I can have, like this nice Lego world when I'm building up bigger and bigger systems. So it's, separation of concerns, divide and conquer. It kind of works. It may not give you the best possible algorithms, but maybe it's robust, right? Like it's a strategy. So here, what we're saying is that, like, let's imagine that someone is able to build an exploration policy that gets to places, right? Like Sham was working on this, and then there are many other works on curiosity-driven exploration. where they give you some policy whose sole purpose is to get to places. I know the question is, okay, if I plug in this policy, can I use it in some clever way to have low regret? And the answer is, of course you can. If someone hands over a policy like that to you, what you should be doing is that you have to switch back and forth between the policy that you really want to execute and the policy that does the exploration for you. So you let the policy to go to places, and once it got to some place, you also have to make sure that you're trying all the actions there. So you're going to take a random action there. And after that, you just follow your policy. So you kind of do these random resets. You use this expiration policy as a way to reset the system to, like a random state and a random action. And if you do this, you can push it through the math, and then you can get some results. If you implement it, so we implemented Polytech as well, even with neural networks, and we tried in some other games like Miss Pac-Man, and it was working well. And I didn't show you the graphs, but it was actually like noticeably way more stable. I never seen Polytech's reward graphs dropping, so it was kind of going up, and maybe like it goes up and stays up. So if you're running these alternatives like DQN or something like that, then it's like suddenly sometimes it just forgets things, and like that's a little bit worrisome. Like I don't really want to use an algorithm like that. Okay, but if you do this exploration enhanced version of Polytech, then on problems where you don't need that much exploration like queuing or Miss Pac-Man, it turns out that it just hurts, right? Like you make the system go to places and then it doesn't have. So that's okay. But in other problems where you really need exploration, I won't have time to explain this. It kind of works. Huh?
Don't you have to kiss a plane now?
I do have to catch a plane, yeah. So I need to really wrap up. So it's kind of weird because I have this mix of different versions of the slides. Anyways, okay. So where are we? So I guess it's kind of interesting to try to decipher of why various ideas that are coming from the deep learning community work, and try to use our tools to understand them. So this kind of the inverse analysis, I call it inverse analysis. So someone designs an algorithm, and you go in and you say, oh, what is the scope of this algorithm? It cannot work always. Maybe it works sometimes because we see good results. So this work is kind of going into this direction, but it's going a little bit further there because it also says that, well, okay, we can take then the theoretical insights and then turn them into an algorithm. So I think that this is kind of an interesting place to be. So where do we go in the future with this? Well, I didn't talk about, I mentioned some of the challenges with the theory. Well, one of the puzzles is that for bandits, we can really make Boltzmann exploration. We can turn Boltzmann exploration into really good strategy. And for MDPs, that's almost certainly not the case. The question is whether there's something that lies in between. And I don't really have a good answer to that. But that's a very, very interesting question. Also, Boltzmann is not the only strategy that you can use in online linear optimization. Indeed, people have been pushing the limits of how you should do online linear optimization. Maybe you should use some other regularizers. We know that there are bandit algorithms that interpolate between stochastic and adversarial words that just change the regularizer. Maybe we can do the same. All right. OK. So with that, let me thank you for staying that late.
Okay, any quick questions for Shava? Okay, if not, I want to thank everybody for coming and have a good trip back. Thanks a lot.